Hi, this is Mick West, and this is an overview of the metabunk.org gas simulator, which you can find at metabunk.org/gas. When you load it up, what you get is this. Now, the reason behind the gas simulator is to demonstrate how molecules of gas form an atmosphere around a planet. This blue thing represents a planet, the white things represent molecules of gas. And it's just simulating some very simple physics. The gas molecules fly around, they bounce off each other, and the planet, gas molecules bounce off the planet. And there's a bunch of parameters you can use to modify it. Now, it starts up in a configuration where the atmosphere more or less stays on the planet. And we've got this graph down here that shows two things. Molecules less than 1 radius away from the planet, and that's this line here, and the temperature, which is the average temperature of the molecules. And if you modify these things, you will see these values change, and if they're not stable, that means generally that the planet is going to lose its atmosphere, or it's in the process of doing some kind of change. But let's go through what we have here. The top two items here are scatter evenly and scatter atmos. Scatter evenly, if you click it, will scatter the molecules evenly throughout the space, and then they'll fly back in again. And you can see we get a big change here in the graph with a decrease in the nearby molecules, a decrease in temperature, and then a gradual increase as it came in, and then it'll kind of oscillate a little bit. Let's skip to the bottom here because there's a useful control here, which is zoom. You can zoom out and you can get a better idea of what's going on. The next thing here is scatter atmos, which tries to do a more atmospheric type distribution of the molecules, and this is what it actually starts with by running this scatter, and you'll see it settles down into an actual stable atmosphere where most of the molecules are within 1 radius. That means about that distance here. Okay, start speed specifies what speed the molecules start at when you do the scatter. So if I do this with a higher start speed, it'll fly all over the place. But you can also bring it down to 0 and redo it, and they'll start not moving. And you can do that through the universe. I use it at 2 or about 2 just to give it some initial realism with moving gas molecules. Wrap just makes the molecules wrap around, so when they go off one side, they come back on the other side. This is quite useful when you get to the planet option, where you can turn off the planet. You can just have the molecules, in a universe, and if you didn't have wrap on, they would just keep going forever, and they'll eventually just dissipate and disappear, and you'd have to zoom way out, and you could still see them. But we normally have a planet, because that's what we're interested in looking at. Let's reset the atmosphere. Now, temperature here is a live number, and it's the same as this red line here, the temperature. It's the average temperature of all the molecules. You can actually grab this and modify it and speed everything up or slow it down, just for a quick little boost of heat, or a quick way of just cooling things off. Particle count, you can add more particles, or you can decrease it to have fewer, which if you have it running slowly, you might want to do that. Particle count does actually have an effect, because the collisions of the molecules has an interesting effect on what actually goes on. So the more particles you have, the more densely packed they're going to be down here, the more collisions there will be. So it's not simply a cosmetic thing, it actually affects the physics. This is just another live view. You can't actually change this. This is the same as the white line here, particles near. Now these two coefficients here, coefficient of molecules 0.995. This is the coefficient, the elastic coefficient between molecules when they collide. Now in an ideal gas, molecules, and especially atoms, will collide perfectly elastically, and that would be 1. But in a real gas, there is energy lost by radiation by molecules, especially when they collide and they change their energy states. So to simulate this gradual cooling down of a gas like the oxygen or the nitrogen in the atmosphere, I set the coefficient of restitution, the elastic coefficient here, to just be a bit less than 1. You can change it to 1 if you like. Quick tip with these: if you move these around like this, it's a little hard to get it to 1, but what you can do, if you click on the number and go up and down, you can more finely adjust it, and you can set it to 1. But you usually have it at 0.9995, thereabouts. The coefficient of planet is the same thing, but for when the molecules bounce off the planet. It's not really that important, but it's there in case you want to experiment with it. Because what we have with a planet is the planet heat. Planets are warm, they're warmed by the sun, or the Earth is, and when the molecules are close to the surface, they get heated up by the surface of the planet, and that's simulated here. And you can kind of see it here with things bouncing around, especially if you zoom in. You see the molecules close to the surface are moving faster than the ones over here, and they kind of transfer their energy outwards. Let's stick a few more molecules in there. So you can increase that amount of heat, and if I zoom out and I turn this planet heat way up, you'll see there's all this heat coming in here, and it starts to make the atmosphere go away. So if we heat up the planet a huge amount, it's going to lose its atmosphere because it's going to introduce too much energy into the gas. You see the heat going up here and then the molecules going down. And let's turn that back down to 0 and just reset it. We need a little bit of heat, otherwise everything just turns into a liquid. And now we've got more particles. There we go. You can also click this revert button here, and it will revert back to the state that you were started in. Anyway, carrying on, planet G is the gravity from the planet. You can increase the gravity and they'll get sucked in more, and you can decrease it to a small amount and they'll float off into space. Well, they won't entirely, though. You see them, they're still being attracted here, and these ones will eventually come back because there's nowhere else for them to go. But if you decrease it a lot, they will tend to fly away. You can see that here. You can change the particle radius, the particle size, and that's, again, it's more than just cosmetic. You saw when I increase it, they kind of spread out a bit more because they're colliding a lot more. And if you decrease it, then they will all kind of come back in again, because bigger particles tend to have more collisions. And this setting the particle radius kind of has a similar effect to having more particles in a way, because you get more particle collisions. Planet radius you can adjust, which I'm not really sure there's much point in doing that, but it's kind of a fun thing to try. You can try it with a very, very small planet, one that's not actually much bigger than the particles themselves. Or you can do it with something that's very, very large. You can zoom in to see what's going on with different sized particles. Let me reset this and just do a scatter. Gas gravity is an interesting one. Let me turn the planet off and turn wrap. Well, I'll leave wrap off actually, but and then I'll do a scatter evenly. Now, if you turn gravity on, every particle gets attracted to every other particle. This is what actually happens in the universe, and over a long time frame, all the gas kind of clumps together in various places to form nebula and stars. But if you do it here, what happens is it just tends to all pull towards the middle, and it kind of forms into a big blob. If we turn down, let's see, the molecular coefficient, that'll tend to cool things down a bit quicker. And we'll turn up the gas gravity, and what will happen is it kind of forms essentially a gas giant, just a big collection of gas molecules that's kind of cooled down enough to stay together. Gas gravity is complicated. Well, it's a inefficient thing to calculate, so it tends to slow everything down, especially if you have a lot of particles. See, if I do a little scatter here and increase the particle count to be a lot, it's very, very, very slow. So I'd recommend not doing it. Let me set it to 0. There we go. Let's reset everything, and that's pretty much everything. So lots of fun things you can try. It's interesting to try to see what is a stable atmosphere. You can see here things are, the number of particles within what R is settling down, and the temperature here has gone up and then it's gone down, which generally means it's going to oscillate a little bit as things are kind of sloshing in and out. But then it will settle down pretty quickly when you've got this essentially friction between molecules, loss of energy with the molecular collisions. And you see here it's settled down. So this is actually a stable atmosphere. And you can see what can you do to make it be not stable. Like if you decrease the gravity, for example, or you increase the heat, or if you set the molecular coefficient to 1, that would mean it's not losing any energy, so it would be constantly gaining energy from the planet's heat, and so it would eventually all fly off into space because things would get hotter and hotter. But of course, the planets and the atmosphere just radiate and cool down, and gets into a kind of equilibrium, which is what happens here. And I think that's about it. You can turn the graph on and off here. You can close these controls, and you can also press the H button, the H key on the keyboard, and it will hide it if you want to do something like take a video with nothing on there at all. Press H again and it will come back. So you could hide it with the graph on if you wanted to do that. And there it is. Enjoy. Oh, and if you have any suggestions or any corrections for my my model, let me know. mick@mickwest.com, and I'll probably be tweaking this a bit, so it might not be the same as you see here, but all the functionality should remain.